Welcome. This is Chemistry 112. We'll be going through today. We'll start with the basics here. We'll go through the syllabus, kind of review the homework and all that, and then get into the lecture. This is because of the nature of this class, we have to do what's called a hybrid lecture. The COVID capacity of this room is 11 people, which is 10 students, including me. So that means since we have over 10 students registered, not everyone can be here in person every day. However, since we're just barely over, if I know some of you are not necessarily supposed to be here right now, or maybe said come Thursday, but that's okay because we're still missing like 2 people here that would have filled us up. But there will, once we get in the schedule of things and the hang of things, there will be room for people to come every day if they so chose. But there is the danger of if everybody chooses to come every day, someone's going to have to be sent home. So keep that in mind. Let's try to keep to our somewhat schedule. But let's keep to our somewhat schedule of when we're supposed to be here. And that will keep us from having too much of an issue. Now, quick reminder. That I'm going to use largely the Google Classroom as a means to post the majority of what we need. Well, that includes right here. I most recently posted up in here a link to the Achieve homework and the class ID, as well as to the YouTube channel, and both just the direct link or some if you want to don't trust the link, you want to look it up. Since not everyone can be here, not everyone will have internet access. I don't know, if something happens, you're on a sport trip, you're on a Renaissance, you're on the road, you can't Google Meet in. I'll be trying to record these meetings as best I can and post them up onto YouTube by the end of the day. While I still want you guys to like interact with the class and whatnot, I will try to edit out things such as like anything that might mention your name directly. So feel free to, if you're either in Google Meeting or in class, let's say, hey, Dr. Evans, blah, 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 and I'll be glad to try to answer your question. So I like to prefer a little bit more interaction than last semester, which was kind of like dead, except for maybe one student. So if you ever have a question, just feel free to interrupt, whether it's via Google Meet or whatever. But okay. But so in here, there's that link. Let's see, scrolling up. We'll see in here, we have access to the syllabus, all the lecture notes, which is what I'm going to be using for the slides, and all the homework assignments are posted on here. This is just for your benefit of, hey, what am I doing on all these things? Most of these will be recorded on Achieve, except for the exams. I'm just putting them all in the same place so you can have a look-see of where everything's being recorded. Now, let's look at the syllabus together real quick. For those who aren't in person right now, that you can get the syllabus on Thursday when I see you next. Okay, so looking at this, so I said that my name, there's office, various ways of contacting me, my email. There, if you're not used to this, last semester we used the Interactive General Chemistry textbook by Macmillan. It's an online textbook. It also comes with the Achieve homework. So if you haven't already gotten that, you can go get the access code from the bookstore. It's a 6-month access code. It includes the homework and the book. If you don't learn good on book, I can lend you a textbook, but the homework for reading will still come from online book. Now, if you have the Barnes & Noble first day thing, you should be able to get the access code. Not, you can still buy it online or whatever. But if you register for the class without paying for it, I think you get like a week or 2 weeks free access until they shut you off. But you have to make sure to pay before then. But that gives you enough chance. If you're going to drop, I guess you can drop. Okay. Since we're Tuesday, Thursday class, right here is a group 1, group 2. It's all except for the 1 day, the spring break. It's pretty much if you're in group 1, which I thought I said maybe, if I remember, 2, 3, 6, maybe A through M. Technically, you're supposed to be here, and then the N through Z was supposed to be here, class 2. But as I said, right now, we still have 1 empty desk, so we would have been fine. But so that would have been like what, like 7 students one class and 6 students the other class. But as I said, there's room for 3 overloads from one to the other, 3 to 4. So take that in mind. But this is the proposed schedule. We're going to try to keep to this as best we can, but it's just the proposed. So the final, there's stuff. Let's see. The big thing here, obviously, if you can't make it to class due to quarantine or sports, try to Google Meet in. If you can't Google Meet in, try to watch on YouTube. So you at least get the general lecture. Obviously, you can probably follow along reasonably well with the notes. But just a little bit extra there to try to help you. The homework. Homework's the big chunk. If you haven't had me before, pretty much you do most of the homework, you do reasonably well on the test, you should do reasonably well in the course. Homework is worth 35% of your grade. Each exam, let's say worth 11 and a quarter. Put 4 exams in there, 11 and a quarter %, and then the final worth 20%. Is it the grade scale is 90% A, 75% to 90 B, 60 to 75 C, 50 below, 50 to 60 D, 50 below F. Really, you have to not do the homework and really bomb those tests to fail. You should be able to easily get a C or at least a B, especially if you do all the work. If you do reasonably well, I've given out a decent amount of A's. Now, so all that's just the syllabus, so that you have in front of you. You get a copy of that, or you can print off on your own. Okay, looking here, going to achieve. You go into achieve. This is the landing page you have here. Obviously, you sign in if you have an account. If you don't have an account, you have to make one. Then, as I said, you put in the course ID. You should find Chemistry 112. So the homework is going to be made up of 3 parts. If you're not already used to this, I've changed a little bit about this since last semester, but a lot of stuff is the same. We have 3 types of homework assignments. We have reading assignments worth 5 points. We have learning curve assignments worth 25 points, and we have assessments worth 50 points. The reading, you click the link, it goes to the little section in the chapter, you read it, that's 5 points. You don't do it by the due date, it's 0 points. There's not any other way to do that, but it's not hard. It really is minimal effort, but you have to do it on time. Learning curve. Learning curve. You have to do a set amount of problems. You have to earn so many points per each section. You will get, depending on the topics, I typically put like, for the amount of topics there, 50 points per topic. You get unlimited amounts of questions over and over and over again until you achieve the score. You could come back and finish it later if you don't want to do it all at once. But you'll keep on getting like, oh, hey, which molecule contains only dispersion forces? Like, oh, CO2. Submit it. Between 15 and 25 points, and you can keep doing it. If you get it wrong, it's worth less points. Blank is the resistance of liquid to flow. Let's see. Oh, let's say this. No, that's wrong. And so I can try again for 5 points. And it just keep going. And you will not be penalized to get it wrong. You'll just let me know, oh, you struggled on this concept. If you need help, you can go directly to the chapter part where you need to do. But you do that, you get it complete, you get 25 points. You do it late, I have to physically check it to see whether it was done or not. I can give you still partial credit. But that's that. It's not really hard. It is a good way to get practice of the concepts of a chapter without worrying about losing any points. But those are due relatively soon in the semester. Just say like the first assignments, which are the reading and the learning curve, January 19th, which is pretty much close to when, not long after we're supposed to have finished chapter 12. I'm trying to make the homework assessment due maybe like a week after we finish the chapter or something like that. So I've changed how I've done the homework where it's due sooner, the assessment's due sooner, but I'm no longer going to penalize you if you don't get it done before the due date. I'm trying to give you a due date so that you can kind of get, it would be great if you could get this done by this time, but you can still go back to it later. I want to try to encourage you to work on it rather than it be you get to the end of the semester and you forget about it, and then you're like, oh crap, it's time for the test, and suddenly all the homework's due at the same time. I'd rather it remind you, oh, this is due now, it's due sooner, and you'll be able to see it's due sooner, even though it won't penalize you for being late. Because otherwise it won't show you what assignment's coming up until the week before it's due, which is why I've changed how the due dates are. Now the assessment, relatively straightforward. There's multiple different parts of it. Like I tried to trim the questions down so there's as few as possible while still getting the best out of it. Sometimes it's select all of the above. Sometimes it's drag and drop or drag them into the proper order. Sometimes there's some math problems. Each of the math problems will have like a certain percentage error rate. Like you can be like 5% off of the desired answer and still get it right. So there is some room for rounding. Please note, you can always check a hint that will hopefully point you in the right direction, and it will not penalize you to use the hint. Sometimes there'll be links on here like, oh, you need to go to the periodic table. However, you get this wrong, there's get a 5% penalty on the homework problem. So try not to just guess, but keep in mind, you can always email me, say, Dr. Evans, I'm struggling on problem number 10 of homework assignment 12. I can go on to your thing and see exactly the problem you're struggling with. So you do not have to just necessarily give up if you can say like, oh, what am I doing wrong? And I can hopefully point you in the right direction. Even if we're not in office hours, it just sometimes will take me a little while to check my phone. But I will get to you and always try to respond to you about that. But that is, so there's 18 problems. If you got all 18, you'd get the full 50 points. If you got 9, you did 9 of the problems, you'd get the 25 out of the 50 points. And as you get more of them done, you'll get more of the points. Obviously, then you get penalized a little bit. You get them wrong, but usually most people can get like 48, 49 of the 50 points without too much trouble. But that right there is your basics of the achieve. All right. So right with that there, and I'm going to actually drag this all the way back over here. And okay. Okay, so with that in mind, we are ready to begin the lecture notes. Okay. So, starting chapter 12. Chapter 12 is liquids and solids. If you remember last semester we went through gases. That's where we stopped. We talked about the properties of gases. We talked about the properties of solutions and all that, and solution phase chemistry. Well, now we're talking about what it means to be a pure liquid, and we're going to talk about the main thing, attractive forces. We've talked about covalent bonds and ionic bonds, but now we need to talk about kind of the bonding structure that happens between molecules, not just within a compound. That's one of the big things we'll talk about. So while we're waiting for this, the basics of this chapter will start with our various different types of intermolecular forces. Like when we talked about ionic and covalent bonds, we talked about intramolecular forces, so forces within a molecule. But intermolecular forces will be forces between molecules. The basic idea of how do we separate a solid, a liquid, and a gas. And the separation between these three depends on the relationship of the intermolecular forces and the kinetic forces, the forces of motion. All atoms are in motion all the time, as so long as they're not frozen at absolute zero, we have some degree of motion. So kinetic energy is always trying to pull them apart. They're always trying to move around and bounce around. Well, the intermolecular forces are what's going to be pulling them back together. And essentially, if we look at gases, remember, we saw that little image on the first part of the first slide, a box with like marbles rolling around at random, bouncing into each other. A gas is just all motion, almost no attraction. They're just bouncing at random. That's what happens when you have all kinetic energy, like no attractive forces. Well, a solid is going to be the exact opposite. It's going to be all attraction, almost no movement. If I have a block of iron on here, and I just put a block of iron right on the table, to all intents and purposes, it looks like it's not moving. If you look on the subatomic level, yes, there's going to be some vibration within the atoms. But if I look on the macroscopic level, it's just sitting there. That's because there's not a lot of energy. All the attraction is holding the molecules adjacent to other molecules. Well, then liquids are kind of in that middle part where there's enough kinetic energy that they can slide and slip over each other, but they have enough intermolecular forces that keeps them from ever really escaping. One guy slips past another molecule, but it makes a bond with the molecule just past it. And so they're like sloshing over each other. They can move, but they're not able to just jump into the atmosphere willy-nilly. And so that's one of the things we'll see. We'll talk about what types of forces are going to be keeping these in place. Come on. Okay. Yeah. As I said, intermolecular forces, we had ionic. We didn't really talk too much about metallic, but there was metallic and there was covalent bonds. These are the intramolecular forces that kept this strong. Remember, intramolecular forces control the reactivity. They're so strong, the molecule has to, in order to break down and do a reaction, we have to break these intramolecular forces. It takes a lot of energy to make a reaction go. Intermolecular forces are like things that control boiling point, melting point, some of the physical properties. How much energy does it take to vaporize? How much energy does it take to fuse, which is melting? All those properties are going to depend on that. Like, to some extent, density is going to be related to these intermolecular forces. Like, how do you make the optimum number of bonds? It's going to be how the molecules pack. How they pack is going to determine the volume, ipso facto, the density. The hardness. A metal that you can hit and it deforms obviously didn't have very strong intermolecular bonds, because you hit them, you're pushing the bonds apart. But you hit it and nothing happens, and you're looking at, well, these bonds are really strong. It's keeping the atoms in place, keeping the molecules in place. Hardness, as I said, is these physical properties depend on the intermolecular forces. Now, last semester, when we talked about gases, we discussed all these forces under the umbrella of van der Waals forces. But we're now going to actually break them down into the various types of forces. Now, these are a bunch of terminology, and we'll go through them, but they basically come down to polarity and dipoles and charges. You have to remember back to the Lewis structures, which is why we have to do Chem 1 before we do Chem 2. We had to get down the idea of what it means to be polar, what it means to have a partial charge or full charge, be a cation, before we got here, because we're looking at magnetic attraction, all said and done. The bigger the charge, the bigger the attraction. So we have what's called an ion dipole, a dipole dipole, a hydrogen bond, and a London dispersion force, which is the weakest one. Sometimes referred just to dispersion forces, or if you wanted to describe exactly what it was and not just the terminology, it's an instantaneous dipole, induced dipole, and we'll describe that in a minute. So, as I said, it's basically opposite charges attract. You bring one magnet close to another magnet, they want to pull together. They want to stick together. Obviously, you can still separate the magnet. You have two really strong magnets. You can pull them apart. It may take energy, but you can pull them apart. You don't need a knife to separate the two magnets. That's because this is essentially the intermolecular. You can't really break the magnet into smaller magnets without using some sort of tool, but you can separate two separable magnets. The stronger the charge, as I said, the stronger the traction. So the greatest attraction is going to come from the greatest charge, which is why ions have the most charge. A full electron loss or a full electron gain is going to be the greatest amount of charge possible. So cations and anions are going to be the most attractive to each other. So ionic bonding, while we said ionic bonding was intramolecular force, it could also be considered an intermolecular force as well. We could consider it when two ions see each other in solution. They're going to be attracted to each other. Now, we can also see ions being attracted to partial charges. Remember, a dipole happens when we have a polar covalent bond. We have a bond where the electronegativity between two atoms are significantly different, so that one atom is greedy and pulls the electrons towards one side. So the electrons that should have been shared equally now become, say, a 60-40 split, 70-30 split, maybe a 90-10 split. So that electron that should be 50% on one atom is now like mostly on the other atom. So we see a shift in electron density. We see the electron over there more than it should, so we see a partial negative, but it's not a full partial negative because the electron doesn't fully belong to that element. So this dipole. So all polar molecules will have our dipoles. Now the lowest type will come from, and the lowest type of attractive forces will come from the non-polar atoms, like organic molecules. We look at gasoline. We look at methane. We look at, iodine or bromine or chlorine or fluorine, these non-polar atoms. What type of attractive forces do they see? Those are going to be the dispersion forces. So, as I said, ion dipole, pretty straightforward. Ion dipole is the basic reason why salts dissolve in water. If it dissolves in water, the reason is this ion dipole attraction. Water has this great dipole in there. So strong, it's going to be hydrogen bonding that we're going to see later. But we have this great dipole. This dipole is going to break up our cation anion interaction in the salt and surround them. And so we're going to see this attraction that we're going to pull in and keep this fully dissolved. This is going to happen in almost every salt solution. There are a few exceptions, which we'll talk about when, remember, we had insoluble salts. But this happens with just about all of them. Now, the dipole-dipole, that's a little bit trickier. Dipole-dipole occurs between two polar molecules. Once again, it's going to be positive to negative, negative, positive. It's just now it's only a partial charge. It's a partial charge, but it's the partial positive of one end approaches the partial negative of the other. And we see these tiny little dashed interactions. It's why many liquids like acetone and ethanol will fully dissolve in water. We're going to get to this term next chapter, but they're said to be miscible in water, which means they dissolve in all quantities. There's no amount of ethanol you can put in water where they're going to separate into two phases. You can put in so much ethanol into water that it's no longer a water solution with ethanol. It's now an ethanol solution with water. They will still mix in all proportions. So, the greater the polarity, the greater the attractive force. So the greater the partial charge, the greater the attraction we can have. But because of the nature of the kinetic forces, these guys will be constantly being broken and constantly being formed as they kind of slosh around. You see that just looking at this quick interaction right here, these three atoms right here, if this at the top atom pulls away up and this guy pulls down, this guy's going to break this bond, but he's going to probably make a bond with this atom as it gets closer. And so it's always going to be moving around making new bonds. It's going to be constantly trapped. Even though it's breaking this bond, it's making new ones. Now, you lower the temperature, thus reducing the kinetic energy of a molecule, you can get to an optimum bonding amount. So you achieve a solid formation and you have things like this. This is in water. The solid of water is going to arrange itself so as to maximize the number of bonds it can see. And so it adopts this hexagonal shape right here, as you see, which this area right in the center of that hexagon is essentially a vacuum. It's essentially, there's no atoms there. And because of this optimal space with the vacuum in there, this atom absence, ice actually takes up more volume and the same amount of water. They're essentially expanding outwards to get as many bonds as we can, the best bonds. And so that's why ice will float on water, because essentially it's adopting a shape that gets the most bonds, as opposed to this compact one that's bouncing around at random. So that's one of those cool things about water, why we could survive, because of this neat thing in water. Now, hydrogen bond. What is hydrogen bond? Hydrogen bond is essentially an extra strong version of a dipole-dipole. It's named for the bond within the hydrogen. When we have a dipole, we are attracting an electron through a bond to one side or the other. Now, the special thing about hydrogen is that, if you remember the atomic structure of hydrogen, it has one proton, one electron. So if you attract the one electron it has through a bond, it essentially has 0 electrons, or some fragment of electron. If you do this with any other molecule, you do this with, say, carbon. Well, carbon still has 6 electrons. If you attract one of its electrons through a bond, it still has 5 remaining. So it's only a percentage. So say it attracts half of electrons, so it's 5.5 electrons divided by 6 protons. Now do the same with, and that's just a small loss. But if a proton, the hydrogen, half of electron gets lost, 0.5 electrons divided by 1 proton, it's 50% of it lost. So hydrogen bonds occur only between fluorine, nitrogen, and oxygen. So those 3 at the top: nitrogen, oxygen, fluorine, and hydrogen. For there to be a hydrogen bond, you have to have either an HF, an HN, and an HO in one atom, and then an O, N, or F in another atom. You only need one HF bond. You only need one HN bond. You only need one HO bond. But you have to have those 3 things. Essentially, interaction between an HOH, OHO, NHN, FHF, or any combination thereof. So, but you got to remember, if this is a liquid and you have an HF or HN or HO, you could interact with the identical molecule right beside it. Like in water. You have HOH interaction here, could interact with another water molecule, the oxygen of another water molecule. I have HF mixed with ammonia. HF mixed with ammonia. You could have the NH bond interacting with the F of fluorine. But I could have the FH bond interacting with the N of ammonia. I didn't draw it on there, but I could also have the HF bond interacting with the F of fluorine, or the NH bond interacting with another N. I could have this, like, this is methanol. Methanol has a CH3, then an OH bond. Now this OH bond can interact with the oxygen on dimethyl ether. This guy has no OH bonds, but it can interact with any guy that does have an OH bond. So if I just had dimethyl ether by itself, we would have no hydrogen bonding. But you put it in with water, you put it in with methanol, and suddenly you got hydrogen bonding, and it's all good. So that's going to be the hardest thing to recognize, but when it is stronger than a dipole-dipole, but weaker than a ion dipole. So the last one is kind of the hardest to understand. It's the London dispersion forces. It's why does nonpolar molecules stick together? Because if there is essentially no interaction, if there's no polarity, why aren't all nonpolar molecules a gas? I mean, most are. Methane's a gas, ethane's a gas, but if you get down to butane, butane's can be stored as a liquid. You get down to hexane, that's definitely a liquid. You get down to, like, say, many of the fats, canola oils, and all that, you can have liquids or even like a solid like Crisco. Why are these guys able to interact and solidify? And this happens to do with their London dispersion forces. Now, remember, within these atoms, an atom has a nucleus and the electron cloud. That electron cloud, the electrons are constantly in motion, circling and spinning around that nucleus at any given time. And they're not ever really going to stop. And there's not really any way of knowing where those electrons are. But probabilistically, we can say that at any given time, there may be a situation where there are more electrons ending up on one side of the atom than another. Or that for a brief fraction of a second, maybe instead of equally distributed electrons, we have 70% of the electrons on one side. It's just a perfect convergence of electron spin that there's more electrons on the left than the right. And what that's going to do is make a dipole. It's only going to happen for an instant because that convergence happens, is gone. For that reason, we call this a instantaneous dipole or a momentary dipole. Now, an atom is going to be constantly having this happen. Just for the fraction of a second is going to happen, but it's going to happen very often because things in constant motion, moving really fast, it's good. This happenstance will happen quite a lot. Maybe not in the exact same place or the exact same way, but it will happen. Well, when an atom has this happen and it's adjacent or close to another atom, it can induce, the electrons swinging to one side for a second can push the electrons of the next atom over into convergence. So what happens is one dipole that happens for a second is going to induce another atom into the opposite dipole. So we have an attraction. And this is what we get the instantaneous induced dipole. This very short-lived interaction that lasts a fraction of a second, but it builds up. It's like tapping the brakes. You're like just slowing the atom down just a bit, not much. You're not slamming on the brakes. You're not using like some sort of parachute to slow yourself down if you're going too fast. But we're just tapping on the brakes just a bit, just a bit. This attraction just keeps happening and keeps happening and keeps happening. And if there is enough of it, we can actually see some noticeable effect. Now, there's three things that will increase this London dispersion force. One is the polarizability. Basically, how easy is it to move those electrons around? How easy is it to get those electrons onto one side? If they're pretty easy to convince and corral to one side, then yes, you're going to have a lot of London dispersion forces. This will have a lot to do with the size. Bigger atoms have more electrons. More electrons mean it's easier to convince the electrons onto one side. You don't have to get like 70% of the electrons onto one side. You get 51, 52% of the electrons. The more electrons you have, the easier it is to get that basic majority. So the more electrons in a structure, the easier it is going to be to convince this instantaneous dipole to occur. So for example, methane, 1 carbon, 4 hydrogens, not a lot of electrons. That's a gas. Ethane, 2 carbons, 6 hydrogens. Propane, still kind of gassy, 3 carbons, 8 hydrogens. Butane, that's when you start to get the liquid form. That's 4 carbons, 10 hydrogens. And you keep going up. Pentane, hexane, heptane, octane, nonane, decane. Heavier and heavier, you're getting more carbon atoms, more hydrogen atoms, more electrons, easier for this attraction to happen. So you're going to have, oh, it's liquid. Oh, the boiling point keeps on going up and up and up because we have more London dispersion forces. The other thing is the shape. The shape is basically how close can one atom get to another atom. If you have like 2 atoms that perfectly will nestle against each other, you can have greater chance of more of these instantaneous attractions. If you have like 2 atoms that perfectly nestle together, you may not see all the atoms everywhere being attracted, but oh, maybe we get these 3 interactions among the whole atom. We don't see interaction there or there or there, but we see it throughout the atom. If you see enough of those, you get your really strong interaction and get liquid. But if you get an atom that looks like this, how do you put this guy against another atom? The best you can do is put it like that. So you can only really have interaction between there. So shape plays a part where how easily are these atoms able to bump up against each other. You got guys with like cactus-like sides aren't able to interact as easily. And so like this is the basic idea of why trans fats and cis fats are like so different. You have trans fats essentially when you have a kink in the fat molecules, if I'm trying to remember, like trans fats can be stored as solids more easily because they can have a closer interaction, and essentially more London dispersion forces let them be stored as a solid. If you had a cis fat, it creates a kink in the molecule that pushes them apart, and they are no longer able to have as close of an interaction, and so they remain liquid. But this size thing also explains, well, if you look at it, fluorine is a gas, chlorine is a gas, bromine is a liquid. Bromine is bigger than chlorine. It's also going to have more electrons and be more polarizable. So bromine has enough London dispersion forces to be a liquid. Iodine is even bigger than bromine, so it has even more London dispersion forces and thus can exist as a solid. So, while London dispersion forces are the weakest, they still account for something. What we'll see, though, is all atoms, no matter what, will have London dispersion forces. The big thing, though, is if the only time this matters is if London dispersion forces is all you got. If you have London dispersion forces and dipole, dipole becomes the overwhelming major force in there. But if you only have London dispersion forces, then those are your only force, so you have to rely on them, and so those take precedent. Quick reminder, from weak to strong. So we have London dispersion forces as the weakest. They are the only effect in nonpolar molecules. So those are the only ones that matter in nonpolar molecules. Next, we have dipole. All polar molecules will at least have a dipole. Hydrogen bonding is the special type of dipole between HF, HO, HN, or another N or F. And then ion dipole, which happens if you have a cation or an anion dissolved into a polar liquid. So real quick, look at this. One of the questions you'll be asked for this chapter is define what forces are present in these guys and then hypothetically place them on increasing boiling point. So the basic thing is the stronger the forces, the higher the boiling point. So if it has an ion dipole or an ion ion, it would have the highest boiling point. If you have hydrogen bonding would probably be next, followed by dipole dipole, and then our basic types of London dispersion forces. So looking here, increasing boiling point. So what would be the lowest? The lowest would be things that are nonpolar that have only London dispersion forces. Some of these you might have to draw. H2O, that's gonna, you got to draw it with itself. So O, H, H. By itself, like we have an OH bond, but it takes drawing another OH to really see that, we can see hydrogen bonding. So that's not going to be pretty low down there. Dimethyl ether. As I was saying, the OCH3, there is a H in there, there is an O in there, but we need an OH interaction. A CH interaction is not good enough. So those are going to have CO bonds. That's going to that's going to be a dipole-dipole bond. And the NaCl, that's the cation-anion pair. Because of that, that's actually going to be one of the strongest. So we're left here with methane and H2. If you're just comparing these guys, both of them are nonpolar. So how are we going to differentiate? The easiest way to differentiate these guys is to say the size. Which one is bigger? A carbon and 4 hydrogens or 2 hydrogens? So carbon and 4 hydrogens is going to have more electrons, so it's going to have more London dispersion forces. So starting from the lowest, hydrogen is going to be the lowest with London dispersion forces. Methane is going to be the second lowest, also with London dispersion forces. Next comes dimethyl ether with dipole-dipole. Next is water with H2O with hydrogen bonding. And sodium chloride is going to be straight up ionic. It has it's a solid. It's going to have to melt before it can boil. So I'm not sure if I actually put the melting points on there, but you look that up. You could boil sodium chloride, but it would be pretty nasty. But so that's how you'd approach it. You'd look at what forces are present in each molecule and then arrange them based on the strength of the forces. So there's a couple of problems on the homework just like that. Now, where we're going to take this is looking at the properties that are caused by these forces. The two basic ones, which can be then linked to the other physical descriptions, are adhesion and cohesion. These are two basic terminology. Cohesion is the ability of a molecule to stick together with the identical type. Like a cohesive team is a team that sticks together. It'd be like the molecule sticks to other water molecules. How well does the water molecules all stick together? Adhesion is the ability of different types of atoms to stick together, but they would still have similar properties. Adhesion, like you glue something on, it'd be you're adhering to the side. So adhesion would be like, how well does water stick to metal, or water stick to glass, or water stick to like a flower petal? And these two types of forces will be present and and it's going to be how we describe a lot of different things like surface tension, viscosity, and capillary action, as we see here. But for them to have a strong adhesion, they have to have similar polarity. So just looking here, we've seen this all in lab. Water, we see it, this little downward meniscus. That's going to be property of both surface tension and, as we're going to discuss in a minute, capillary action. The idea that the water is adhering to the side of the glass. It's going to stick there, but gravity is going to be pulling this down. Gravity is going to be pulling this down. So otherwise, they would keep, as we're going to see in capillary action, it's going to keep raising up that glass. So gravity is pulling it down, but the adhesion onto the glass allows us to scooch up a little bit further. Now, mercury, obviously, we're not going to see this more often because they take a lot of mercury and it's pretty toxic and kind of expensive. But mercury has a convex meniscus, meaning it doesn't want to be on that glass. It's actually pushing itself away from the glass to try to get as far from the glass as it can. So it's pushing itself up. So the meniscus is the opposite because they have good cohesion, poor adhesion, while water has a good cohesion and good adhesion. Just looking at a rose petal. You ever see a rose petal in the morning when it's all dewy? The dew beads up like this because of adhesion. The rose petal has a waxy surface. That waxy is nonpolar. There is not a good interaction between the water and the surface. So that water is going to try to minimize the contact with the rose petal. So it's going to bead up rather than spread out. It's going to bead up on there because the interaction between the rose petal surface and the water is not good. So the first thing is viscosity. Pretty easy. It's basically the resistance to flow. How well does the solution flow? If I pour it, how well does it pour? Does it stick together? You ever try to pour cold syrup? Like try to pour some sorghum. Try to pour that cold sorghum. It's very slow. You got honey. Those are very what we'd call viscous solutions. Hydrocarbons and water are actually not very viscous. They will flow relatively easily. It's a case of essentially extreme cohesion that prevents this from pouring. Though, because this is an intermolecular force, and intermolecular force is always fighting a kinetic force, if you heat this up, you can actually decrease the viscosity. Hot syrup pours more readily than cold syrup because you're essentially giving it more kinetic energy, better able to break up the intermolecular attraction. Now, surface tension is an example of the cohesion when presented with a boundary of like a solid, a liquid, or gas. It's basically the molecule is being pulled into place. The water molecule is the most excellent example that they stick together when confronted with air so well that they can withstand minute forces such as insect feed or even an overflowing brim. Like you have a cup of water filled to the brim. You can keep adding small little things so that the liquid surface of the water is raised over the brim and it still doesn't pour out immediately. You have to break this force. It's basically that these molecules in the center here all these molecules are essentially pulled in all directions simultaneously. This molecule A. This molecule B is only pulled down. There's no pull up. So because there's no pull up, it can essentially apply a force directly upward against the external pressure. So if you push down on the molecule on the surface, because it's being held by all the other molecules, it can push back, trying to maintain the shape. Now, insects have feet with usually non-polar treads, so that you have a poor interaction with the water, and so they're able to actually walk on the surface because of this interaction. Now, a really neat trick to kill, say, mosquitoes and, well, a lot of other type things is like mix, say, some sugar or something into the water, but also mix a little bit of soap. The soap is actually going to break up the hydrogen bonds within the water and thus disrupt the surface tension. So when, say, a fly tries to land and get a drink, it will sink and die. Now, be careful, because you could also kill bees the same way. And the risk of good pests versus bad pests. And one of the final properties is capillary action. It's the ability of a liquid to move upward against gravity within a narrow tube. It's the basic adhesion and cohesion effect. The liquid essentially sticks to the side. It sticks to the side of the glass and tries to pull the rest of the liquid with it. So it pulls it up. It's kind of like an inchworm pulling up the glass tube. Gravity is constantly trying to pull it back down, but it sticks to the side. It pulls the center up by the surface tension. It sticks a little bit more to the side, and it pulls the center up with the surface tension. And it will keep doing this until the adhesive forces and surface tension pulling up are countered by the force of gravity on that tube pulling down. And so the surface area of that tube is going to depend on how far this can go up. This big tube makes it this far. This thinner tube makes it a little bit higher. As you get thinner tubes with less surface area, the liquid can move higher and higher up those tubes. But this is, among other things, one of the ways that trees use to move water from the roots to the leaves. There's some other forces in there, but it definitely aids this motion. So one of the major things we will talk about this chapter is our phase changes. We talked about this kind of briefly in thermodynamics, that the energy it takes to change from a solid to a liquid. But we're going to look at it a lot more intensely here, that the enthalpy that it takes to get from a solid to a liquid or a liquid to a gas. We can measure these as an enthalpy value. Remember, our energy, our heat-based energy. If we're melting, we call that the heat of fusion, because we can go both ways, liquid to solid or solid to liquid. So when we're fusing things together, we're taking a liquid and putting it into a solid crystal structure. Enthalpy of vaporization would be the energy of boiling. We're vaporizing sun, but it could also be the energy of condensation. So going liquid to gas, gas to liquid. Once again, these could be positive or negative values based on the direction of this change. And they can be measured in kilojoules per gram or kilojoules per mole. So it takes energy to melt a solid. Then by proxy, it must generate energy to freeze a solid. It takes energy to boil a liquid, so it must release energy to condense a liquid. There's one other thing we can look at. It's the energy of sublimation. Sublimation, remember, is energy it takes to turn a solid directly into a gas without passing through the liquid phase. It's not just melting and boiling, but doing them at the same time. So the solid just poof goes into the gas phase. And the energy of that is actually going to be the sum of the two previous energies. But that is done usually under certain conditions. Certain things are easy to sublime, certain things are a little hard. If you've ever seen dry ice, which is frozen CO2, that is the most common case of sublimation if you've ever seen it. It will boil off into the gas phase. It's really cold, and unless you have a certain freezer, it will naturally boil off. So you won't have any liquid CO2. You'll just go straight back into the atmosphere. Now, this is kind of an issue. As you may or may not know, our current vaccines, Pfizer and Moderna, at least one of them, I think Pfizer, needs to be kept at sub-zero temperatures, and they have to use dry ice to try to store it as they're trying to transfer. So trying to get enough dry ice and keep it cold enough and keep it safe is one of the big problems with trying to transport this and keep everyone safe and keep the vaccine useful as long as possible. Now, we're going to look at some of these heating curves. A heating curve essentially looks at temperature versus energy input. Temperature versus energy input. So the temperature of our solution at any given point versus how much energy got put into it. So we're going to look at here, this heating curve has a couple different things there. You can break this down into 5 distinct phases. Phase 1 right here is when you're heating the solid. Whenever it plateaus is when you're doing a phase change. So we have heating the solid, we're melting the solid, we're heating the liquid, boiling the liquid, and then heating the gas on that last thing. As you notice, for phase 1, 3, and 5, the temperature is changing with changing energy. So, like, how would we calculate those? Would calculate those how we did the same in thermodynamics, the Q equals MCAT equation. Q equals MC delta T, where you have the heat equals the mass times the heat capacity times how much temperature do we want to change. Now, the two plateaus, as I said, are the melting and freezing region. That is a set energy per mass. During that region, hypothetically, temperatures should not change. Temperature should not change. So while there is liquid existing and solid existing, the temperature should be essentially the same. So if I drop ice into a glass of water, as that ice melts, the water will chill down to 0. And until all that ice melts, the water should also be 0. The same way, if you're trying to boil a pot of water, once you get to boiling point, so long as there is water in that pot will never go over 100. That pot should not be going over 100. So once you achieve boiling, you do not have to continue to heat intensely unless you're trying to make steam, or unless you have something like a pressure cooker, which we will get to a little bit later, not right this second. All right. Now, another property we'll see has to do of these cohesive and adhesive forces, has to do with vapor pressure. So what is vapor pressure? So essentially, as a liquid exists, we have a competition between the intermolecular forces and the kinetic forces. The kinetic forces want the solution to escape into the gas phase. They want to break apart, break away, escape. The intermolecular forces are trying to keep it together, maybe achieve a solid phase. And we have a constant competition. Now, because the molecules are constantly making and breaking intermolecular forces at any given time, they're sloshing around. Well, what happens when a molecule on the surface sloshes a little bit too hard towards the surface area? It can escape into the gas phase. It bounces out of the liquid and into the gas phase. Now, this gas, when it's bouncing around above a liquid, can bounce back into the solution and plunge back in and get trapped again. But at any given time, so many molecules of the liquid are escaping into the gas phase. And so many molecules of gas are going back into the liquid that it's going to generate a set pressure based on the amount of kinetic energy. This pressure is the vapor pressure. This really only depends on the temperature of a liquid. Water has a set vapor pressure depending on what temperature the water is. So remember, temperature and kinetic energy are directly related. So the higher the temperature, the more kinetic energy, the more likely the molecules are going to have energy enough to escape. And so that's what we have here. Now, here's a cool thing. If you have a closed bottle, a closed container, we're going to achieve the vapor pressure, and you're going to a constant vapor pressure. For every molecule that you'll get to what's called an equilibrium state, a steady state. Equilibrium, as we'll see later on, does not mean everything stops. It means we get a steady state where for every forward reaction, we have equal amounts of reverse reaction. In a closed container, you'll get to a point where every time a liquid molecule escapes into the gas phase, a gas molecule will bounce back into the liquid phase at the same rate. So essentially, the pressure becomes constant. However, in an open container, the liquid will eventually all escape into the gas phase. So if you leave a glass of water on your table for a couple months, a year, it's eventually going to go dry, because it may take a while, but the liquid will escape into the gas phase, and if it's not enclosed, it could bounce away into the atmosphere, and you'll be just fine, and it won't come back. Now, liquids that rapidly evaporate are said to be volatile. Those that are hard to vaporize are called non-volatile. But essentially, volatility and high vapor pressure are signs of weak intermolecular forces. So if these gases can easily break free from the liquid, they're not being held there very strongly. Things like ethanol and acetone, organic compounds, what we use to clean in organic class, are typically volatile. If you can smell them when you're around them, usually they're pretty volatile, because what you're smelling is trace molecules escaping from the liquid into the gas phase, and you're breathing in those gases. You're like, oh, you open the bottle and oh, that has a nice organic smell to it. You're smelling the volatile molecules that have escaped into the gas phase. Now, that'll be where we'll stop for today. On Thursday, we will continue from here, I hopefully I'll see the remaining students. Keep in mind, if everyone shows up, we will be in a little bit of trouble because we have 13 students and only, I'd like to say 1, 2, 3, 9, 10, 11, 12, yeah, 13 students and only 10 seats. So keep in mind, but once we get things kind of a little bit more sorted out, we should be able to figure out who best wants to come in every time.